Hello everybody, this is a video going over the Unit 3 practice exam for Physics 252. This is the key that you have access to on Canvas. I'm just going to go through it in more detail because we didn't get the chance to do so in class. So let's first take a look at number 1. We have a 1 centimeter long, 4.0 millimeter diameter gold wire segment that carries a current of 250 milliamps. Well, number 1, what's the current density in this wire segment? So the electron or the resistivity of gold is not something that I would expect you to have committed to memory. This is a value that I looked up in our textbook. So that's 2.4 times 10 to the negative 8 ohm meters. So we could use the current density expression that we used in the current and conductivity lab. That's just the current divided by the cross-sectional area. So we have to remember to convert from millimeters to meters and also to take this diameter and cut it in half. So that's where 2.0 times 10 to the negative 3 meters comes from. Here we end up with something that would round to 2.0 times 10 to the 4th amps per meter squared. That unit doesn't break down into anything nicer. It's just left as a ratio. So the resistivity is related to the resistance, but they are not synonymous. So if we look at the actual length of the wire segment in addition to its cross-sectional area and its resistivity, we can calculate the resistance in ohms. So we have the resistivity times the length divided by the cross-sectional area. That gives us a very small value, which when you think about it makes sense because you want to think of this wire as not being its own source of a good deal of resistance, but instead something that just allows charge to move from one place to the next. So we have 1.9099 times 10 to the negative 5 ohms, which you could leave in ohms. I just expressed it in micro ohms. So 19 micro ohms would be the resistance of that wire segment. Number 3, we don't know anything specific about where this current is coming from just yet, but we know that its value or its magnitude is 250 milliamps. So if we turn that to amps, that's the equivalent of 0.250 amps. And an amp itself is just a coulomb per second. So I can rewrite that current as 0.250 coulombs per second. And since I know that every individual electron is responsible for 1.60 times 10 to the negative 19 coulombs, the ratio tells me how many electrons are entering the wire each second. So because this is each second, I didn't have to do anything more with the denominator. But if this were, let's say, each 5 seconds or each 5 minutes, perhaps, then you'd have to convert the time into the appropriate unit. But here I end up with a very large volume of electrons, which makes sense when you remember just how big a single coulomb is. This is 1.56 times 10 to the positive 18 electrons entering that wire every single second. So moving on to 4, how much energy has been lost for each coulomb of charge that travels from one end of the wire to the other? This is most closely related to the charge escalator model that we use to understand how the charges that you can imagine are emanating from the positive terminal of the battery end up getting the energy that they lose as they move through the rest of a circuit loop. So because the wire is not ideal and it has a very small amount of resistance, the current 0.250 amps for this resistance value is going to result in a very small but non-zero voltage drop or a potential difference. So when you calculate that, you get 4.7746 times 10 to the negative 6 joules per coulomb. And here in green, I'm just showing how these units break down. I have current times resistance, so amps times ohms. The ohm is itself defined as the volt per amp. So that's going to get me to volts. But since the way that this problem is phrased, it relates energy and charge to one another. I just expanded that volt into a joule per coulomb. I could have just left it as volts in this last step here, but it just reminds us of exactly what a volt measures and what it means. So the next set of questions let go of the system that we worked with in questions 1 through 4. We're starting over fresh with 3 resistors, 40 ohms, 90 ohms, and 120 ohms that are connected in parallel to a 9.0 volt battery. So this would be the case where this circuit is one whose equivalent resistance I can figure out. In other words, I have just a single battery. I have a group of resistors. I can figure out what REQ is for this entire circuit. And probably most importantly, this isn't complex. There aren't parts of this circuit that are wired in series and other parts that are in parallel. It's just all parallel. So this is what that circuit would look like. And we've seen this sketched in a couple of different ways, but namely, if you want to go back to the parallel circuit summary slide that's in the Fundamentals of Circuits chapter, it shows a parallel circuit rendered like this. So there are multiple junctions. That means that each one of these resistors has its own connection to the battery, so they don't depend on one another. The equivalent resistance for a parallel circuit is going to be the sum of the reciprocals of the resistance values. So I have 40 ohms, 90 ohms, and 120 ohms. We can use 360 ohms as the common denominator. So 1 over REQ is 16 over 360 ohms, where the unit is going to stay in the denominator until this step here, where you take a reciprocal, because you are almost never going to be concerned with the reciprocal of the equivalent resistance. Instead, you're going to be concerned with the equivalent resistance itself. So that's 360 divided by 16. That rounds to 23 ohms when you apply 2 sig figs. The current through each resistor, this is a problem that we could solve using our equivalent resistance that we calculated in number 5, but it's not required. And the reason why it's not required is because I actually have 3 intact loops that just overlap one another. So I can take the battery and the 40 ohm resistor as being one of those loops, the battery and the 90 ohm resistor being the second loop, and then the battery and the 120 ohm resistor being the third loop. So I'm using Ohm's law here, but not applying it to the entire circuit as a whole, but just individual loops in the circuit. So I have the ratio of 9 volts over 40 ohms. That gives me 0.225 amps, and to 2 sig figs, we would take that to 0.23 amps. Doing the same for resistor 2 would give me 0.10 amps, and then for resistor 3, that's 0.075 amps. The current through each resistor, I1, I2, and I3, they'll have to add up to the battery current. So I don't have an individual question for that here, but we can determine exactly what that would need to be just by adding 0.23, 0.10, and 0.075. You should add them in their unrounded form wherever possible. So that battery current is the same as what I would get if I took Ohm's law and applied it to the entire loop. So if I have my 9 volt battery, so that's this is indicated as an EMF. That is just like a shorthand for saying that this is an ideal battery. And if instead of having these 3 individual resistors together, if I had one equivalent resistor that had value 360 over 16, then the current produced by the battery would just be 9 volts divided by the ratio 360 over 16. And the value I'd get there is exactly the same as the sum of I1, I2, and I3. So that's a different way that you could have answered question 6 by using your answer to question 5. But like I described earlier, that's not a requirement for a parallel circuit. So number 7, the voltage drops across each resistor just by virtue of the fact that they are arranged in parallel. That means that each resistor gets the full 9-volt potential difference. So the currents are going to be different in each branch because R1, R2, and R3 are not all equal. But the delta V across that branch, or each branch, is going to be the same. That's just a property of how parallel circuits work. Next, for the power dissipated across each resistor, there are 3 different expressions you could use for this. I just chose current squared times the resistance. Because I already know what the current is, we calculated that in question number 6. But remember, your other option would be to take the current through each individual branch and multiply it by the voltage drop. Your third option would be to take the square of the voltage drop across each resistor and divide it by the resistance. All of those paths lead you to the same conclusion about power dissipation. So just using the method that I used, current squared times resistance, that's going to give you something that has units of amps squared times ohms. And if you go back up to our, I think, number 4 discussion, when we talked about how the volts, the amp, and the ohm are related to one another, what you'll be left with here is just a joule per second, which is the same as a watt. So to 2 sig figs, this is 2.0 watts. I can apply the same logic or the same process to each of the other resistors, and I end up with 0.90 watts and 0.68 watts. So I think to save space, I didn't put a question on this page about how to calculate the power that's delivered by the battery, but all I would need to do that is to take the total current, so 0.225 amps, added to 0.10 amps, added to 0.075 amps, and multiplying that by the EMF, which is 9 volts, will give me the sum of these individual powers. This is really just the law of conservation of energy, but applied in a kind of specific sense for an electric circuit. So for the next few, let's imagine that we've got the same 3 resistors and the same battery, but we just rewire the circuit so they are in series. So in this case, each resistor is depending on the other ones in order to keep the loop intact. I've got a battery current that's going to go through this loop clockwise. And I know that just because I drew this battery with the positive terminal up. If I flipped the battery around, then the direction of the current would go to counterclockwise. However, the direction is not really what's important here, but instead the magnitude. So for a series circuit, I have to figure out how to express the equivalent resistance first. I can't just apply Ohm's law individually to each of these resistors because each resistor doesn't have its own unique current. It's a shared current. That's another way of saying that this 9-volt battery is going to produce a different amount of current based on whether it's trying to power these 3 resistors in series versus the same 3 resistors in parallel, as we saw them in the previous set of questions. So for series resistors, the equivalent resistance is literally just going to be the sum. So if I had a 250 ohm resistor, I could connect it to this 9-volt battery, and it would produce exactly the same amount of current as what we have in our actual circuit. So for the current through each resistor, just by virtue of the fact that this is a series circuit, they're all going to have the same current. There are no junctions for current to split off. So whatever goes through the 40 ohm resistor is going to be exactly what goes through the 90 and the 120. I can figure out what that is by using the loop rule. So that's another term for Ohm's law applied to the entire circuit. So I take the EMF because I know for sure that the voltage drop across each individual resistor is not going to be 9 volts. But I know combined, if I go through the entire loop, the voltage drop is 9 volts. So 9 over 250 gives me 0.036 amps, rounded to 2 sig figs. So now I can take that current that I know applies to each of the resistors and figure out how that 9 volts that the battery is providing is lost as I go across each resistor. If I put in 9 volts, I have to be able to find where I lose 9 volts. So this is Ohm's law applied to just the individual resistors. I know the current and I know each resistance value. So to 2 sig figs, the potential difference across resistor 1 is 1.4 volt, across resistor 2 is 3.2 volts, and across resistor 3 it's 4.3 volts. If I add these together in their unrounded state, then I'm going to end up with 9.0 volts. So I put in the same potential difference that I can see being lost across each resistor. Likewise, to find the power dissipated, I could use I squared times R, I could use I times delta V, or I could use delta V squared divided by R. But all paths will lead me to the same powers for each resistor. So when I take these 0.052 added to 0.12 added to 0.16, I'm going to get the same value as I would get if I took the current, so 9 over 250, and multiplied it by 9 volts, the EMF. Now for unit 3, for this new circuit, these are the same elements. I have a 90 ohm, a 40 ohm, a 120 ohm resistor. I have the original 9 volt battery, and now there's a new 12 volt battery, and I have a switch. So please ignore this 40 ohm resistor label. That's just something I forgot to move out of the way when I was creating this image. So I have 2 batteries, and I have a circuit for which when the loop or when the switch is closed, I can't just simplify it. I can't figure out what REQ is and then just treat this exactly the same way as we treated our parallel circuit and our series circuit. So here I'm going to have to use combinations of the junction rule and the loop rule. So first, with our switch open, there will be no current through the 120 ohm resistor. So it's essentially inactive here. And I have 2 batteries that are lined up positive terminal to positive terminal. So instead of adding the 12 volts and the 9 volts, I'm going to find the difference between these two. It's like sending a charge from the negative terminal of the 12 volt battery up to the positive. So it has a potential difference of positive 12 volts, and then sending a charge backward through the battery so that there is a potential drop this time of 9 volts. So combining those is easy when the switch is open. I just have a 3 volt. So I can imagine replacing my 2 batteries with a single 3 volt battery, and again, just completely overlooking the 120 ohm resistor because there's no current when that switch is open. So this is now a series loop, which means that my first step is going to be figuring out what the equivalent resistance is. So that would just be 130 ohms. I just take 90 and add 40. And the battery current is going to be 3 volts divided by 130 ohms. So to 2 sig figs, that is 0.023 amps. And for the labeled currents in this image, I3 is the name we've reserved for the current that would be moving through the 120 ohm resistor, but I know that's 0 as long as the switch is open. So that means IBAT is equal to I1 and I2, not equal to I3 this time. When the switch closes, now I3 is going to go from being 0 to non-zero, and the entire current produced by this group of batteries is going to be different than the 0.023 amps that we solved for previously. So in order to figure out exactly how they compare to one another, let's take a look at the three currents and how they are interacting with the two junctions here. And I'm going to choose the one at the bottom just because it's easier to see how these currents split. So let's assume that the switch is closed at this point. I have I3 that heads to this junction right here at the bottom. Some of it's going to go through the 90 ohms, some of it's going to go through the 40, but I know that I3 is going to split into I1 and I2. That's another thing that I could evaluate up here at the top by imagining I2 heading into this junction up here at the top. I1 heads in as well. So whatever goes through the 120 ohm resistor, that third current I3 is going to be the sum of the two. For the loop rule, I used loop A and loop B. And again, when the switch is closed, I could have done like maybe the left side loop and then the outer loop, or I could have done the right side loop and the outer loop. The only constraint here, or the only criterion that you have to fulfill, is that all of your resistors are counted at least once. And you know that at least one of your resistors is going to be counted twice. So because of the choice that I made to do left side loop and right side loop, it's going to be the 120 ohm resistor that gets counted twice. So starting at the positive terminal of the 12 volt battery, the negative terminal of the 12 volt is where I'd want to start. So I have a positive potential difference of 12 volts. As I move through this loop, I3 is the same as the direction that I've chosen because I'm going clockwise. So I3 times 120 is something I'm going to subtract off. At this point here, I1 is something I can apply to that 90 ohm resistor. So I'm going to subtract 90 ohms times I1, and then I'm back to where I started, so that's 0. And just as a reminder, in order to determine whether you need to add or subtract these potential differences, just take a look at the direction of the current and how it compares to the direction that you've chosen to work through the loop. If it's the right way, or to say it another way, if the directions agree with each other, it's going to be a negative. If the directions disagree, it would be a positive. So we don't have an example of the directions disagreeing here, but if you look at the solved problem from our class notes, Fundamentals of Circuits Part 2, we did have an example where we had to treat a potential difference as a positive. So getting back to this, we have loop A sorted. Now for loop B, I'm going to start at the negative terminal of the 9 volt battery and work my way through counterclockwise. So it's a potential gain of 9 volts going from the negative terminal to the positive. Moving through this 120 ohm resistor, it is now going to be a potential drop. So I have a negative 120 ohms times I3. Getting to the 40 ohm resistor, now I'm moving with the current. So this is going to be I2 times 40 ohms subtracting. I don't know why I wrote those in the opposite order there, but the point is that the 9 volt is the only positive delta V. The other two are going to be negatives. So now I've got a system of equations, Roman numeral 1, 2, and 3. I only have 3 unknowns, I1, I2, I3. So you can solve that system however you like. What I did here was I combined 1 and 2 so that I could eliminate I3. So I have a statement for I2 that just depends on one of the batteries, a combined resistor, and I1 along with the 120 ohm resistor. I did something similar with equation 1 and equation 3 so that I could eliminate I3. And I have now a second expression for I2, so I can set those two equal to one another. And that's exactly what I do here. So 12 volts minus 120 ohms times I1, all that divided by 120. That was the first expression we derived. The second one is on the right-hand side here, 9 volts minus 120 ohms times I1 divided by 160 ohms. I can just solve this for I1, and I end up with the ratio 7 over 160. So that is 0.044 amps when you apply 2 sig figs. And at this point, now I have two choices or two options that I can use to figure out what I2 is, because my first combined expression just has I1 and a whole bunch of variables. So I can plug I1 in here. And then, I'm sorry, a whole bunch of constants is what I should have said. And then for my second expression, I likewise have a bunch of constants and then I1. So either one of those methods would give you the same ratio. If you end up with something different, then that means that you need to go back and check your algebra somewhere, because they should agree with each other. But this gives me 0.023 amps. Once I have I2, I know that I3 is just going to be the sum of I1 and I2. So I use the junction rule. That's equation 1 further up on the screen. And I have 0.067 amps. That is the current or the current that I have labeled as I3. So there's not a question that asks us for this here, but since I do know I1, I2, and I3, I also have a way to express I bat, so the current produced by the combination of these two batteries. That is something that I could use to figure out what REQ is, because I don't have an arrangement that I can just simplify as easily as I could for the purely parallel and purely series circuit. Moving on, we have a new scenario, 2 long parallel wires that are separated by a known distance. We know the currents through each wire. We want to figure out the magnetic field at a location P. So point P is 150 millimeters away from the 12 amp wire. It is only 30 millimeters away from the 8 amp wire. So what we can do is apply the Biot-Savart law for a linear wire, so one that's not bent into at least a partial curve or a partial loop. So it's just a matter of calculating the magnitudes of the magnetic field at location P and correctly identifying their directions. So that's what this diagram up here is showing us. This is like a bird's eye top-down view of this situation. And applying the right-hand rule shows that because these currents are anti-parallel, both magnetic field vectors are going to point toward the bottom of our screen at point P. So they're going to combine as opposed to partially canceling each other out. So the net field would just be the sum of these two magnitudes oriented down, and this is down with respect to our page. The magnetic field vector on this plane would just point toward the lower end of the plane. So you get something that you can express as 69 microtesla or 6.9 times 10 to the negative 5 Tesla. Next, we're going to examine an electron moving with a known speed at a right angle to a magnetic field with a known strength. So the fact that the electron is moving at a right angle to the field just tells us that the entirety of the B vector is perpendicular to V, so I don't need to break it down any further. In other words, I know that the angle phi that I am considering is going to be 90 degrees. So I have chosen arbitrarily what the direction of B and V are. And all I really need to know is that they're perpendicular to one another. So I arbitrarily selected B to be oriented toward the right side of our screen. That means that my options would be either straight down or straight up for the velocity vector. If I wanted to keep both B and V in the plane of the page. So it's an arbitrary choice because I'm asking you just for the strength of the force. Whichever decision you make will be appropriate. So I have the fundamental charge, that's a known. I know the mass of the electron. So the magnetic force on the electron is just going to depend on the strength of the field it's moving through, the velocity of the electron, and the charge. So again, the fact that they're 90 degrees apart is something that was given to us here because it's a right angle. So I know the force is going to have a strength of 2.8 times 10 to the negative 14 newtons. And you would also recognize this scenario as the same one that we encountered in the E over M lab when we found the charge to mass ratio for the electron. So this electron would feel a force that is either oriented directly into the plane of the screen or directly out. And we can use the cross product version of the right-hand rule to figure that out. So if you line your thumb up with the direction of the velocity vector, if you line your index finger with the direction of the magnetic field vector, you'd find a force vector that's coming right out of the plane of the screen. And that means that this path that the electron produces is not going to be linear. Instead, it's going to be a circle. So we can apply some radial force logic from semester 1 to figure out exactly how big that radius or how big that circle is. So I have m times v over q times b. These units are kilograms and meters per second in the numerator. We have Coulomb Tesla in the denominator. And a Tesla is a Newton divided by an amp divided by a meter. And I split this amp into coulombs per second because I know ultimately I'm going to want to cancel one of the coulombs that shows up in the denominator. And the Newton is kilograms times meters over seconds squared. So when you cancel out all these units, the only thing that actually makes it through is this 1 meter in the numerator. So applying sig figs, this is going to be 0.081 meters or 8.1 centimeters. Number 18 deals with the scenario that we talked about briefly in our magnetic field chapter in the first half of the notes, I believe. So we have an estimate for the magnetic field, the Earth's magnetic field at the equator. And I somehow didn't superscript this negative sign, but this should be 5.0 times 10 to the negative 5 Tesla. And it's nearly horizontal, directed from south to north. So if you had a current carrying wire that had a known length and a known current value, you would experience different forces on that wire depending on whether it was oriented with the planet's magnetic field or against it. So for our east-west orientation, this would be like orienting it against the planet's magnetic field. So I just chose this magnetic field vector being oriented toward the right so that I could say that north is on the right-hand side of this little diagram. But the current is going to be oriented into the plane of the page here because it's going from east to west. So east would be like in the foreground of our screen, west would be penetrating into the screen. I can use the magnetic force expression. So when we use this further up here, it was charge times the velocity times magnetic field times the angle. The angle is going to be 90 degrees for us again, but I can take Q times V, which was just charge times velocity, and write that as current times length. That's also an expression that's derived in our magnetic field notes if you need a refresher. So 20 amps times 25 meters times the field strength means that the force on that current carrying wire is going to be non-zero. It's small, but it is not zero. That's the point. So it's going to be directed straight down. So this is toward the surface of the planet. And you can use the cross product version of the right-hand rule in order to determine why that would have to be the case. Your thumb would have to go in the direction that a positive charge would move. So that would be into the plane of the screen. Your index finger would have to go in the direction of the magnetic field, which the way I drew it is toward the right. So that means that your middle finger would point toward the surface of the planet. So that's where down comes from. And then for north to south, in this case, you would have your current carrying wire lined up with the planet's magnetic field. So there would be no force that would deflect it. In other words, the angle between your velocity vectors and the magnetic field would be either 0 or 180. Both of those would yield a force of 0 newtons. Next, we have a coil with a known number of turns and a known radius. How quickly must a 0.65 Tesla bar magnet be inserted into the coil to induce an EMF with a magnitude of 0.5 volts? This is a Faraday's law problem, and you can't think of this as a Lenz's law problem, but all I'm asking you about is the magnitude of the induced EMF. I'm not asking you about the direction. So if you can determine the change in flux and relate that to the induced voltage, you're done. You don't need to know whether the north pole of the magnet's being inserted into the coil or the south pole is. I just drew it with a north pole going in, but a south pole going out at exactly the same speed would produce exactly the same magnitude EMF. So to determine the magnetic flux, I need to know the number of turns, the magnetic field produced by the bar magnet, which is a constant, and then the cross-sectional area. So that's the same as taking that number, that field, that area, and multiplying it by the cosine of theta. This version here is the one that kind of references the fact that we can sort of think about the plane of the coil as being something that has a vector character to it. So I'm looking at a dot product, but I have N, I have B, and then the area of that circle would just be pi r squared. So I have 0.2042, and this is Tesla meters squared, which is itself the Weber. I didn't turn it into Webers because I know I'm going to need to break that unit down in the next step, so I'm just leaving it as is. And I also know that the change in flux is going to go from something to nothing. Or actually, since I have the magnet being inserted into the coil, it's going to go from nothing to something. But the change in flux is going to be final minus initial. So delta phi is also 0.2042. So now here, the amount of time that it takes in order to change the flux by this magnitude is ultimately what's going to determine how large an EMF is induced. So this is Lenz's law, I suppose, written with the just for magnitude. And the time required would just be the change in flux divided by the induced EMF. I have the magnitude of the induced EMF, so this gives me 0.4 seconds. And I've got a unit breakdown that shows where that comes from, because it's not at all obvious when you look at it at first glance. So a Tesla can be written as a Newton second over meter coulomb. You can also take the second that shows up in the numerator and pull it back down into the denominator of the velocity unit to see how you get there. A volt is a joule per coulomb. So if a joule is a Newton times a meter, and volts are in the denominator, I can write that as coulombs over Newton meters. And then area is just going to stay in square meters. Do some unit cancellation. The only thing that makes it through is is this second that's in the numerator of the Tesla. So that's how we know we have time units we're working with. We have an ideal transformer here in question 20. All I know is that the secondary coil has 275 times as many turns as the primary. So I don't have a given value for N1 or N2, but knowing the ratio is enough. The fact that the secondary coil has 275 times as many turns as the primary means that this is a step-up transformer that will make a small voltage large. So I drew a quick sketch here with all of my primary information on one side, all of my secondary information on the other, and I'm trying to figure out what the current in the primary coil is. So in order to do that, I need to know something about what the voltage on the secondary coil is. And if the primary is connected to a 120 volt source, V2 would just be 275 times what that primary voltage is. Because of the way I have this written out, N1 cancels. So this is 33,000 volts. I can use that now with this power relationship. If I multiply both sides of what I have written here by V1, I have I1 V1 which is a power, being equal to I2 V2, which is also a power. I've given a secondary current that's in milliamps. So depending on how you want to express the primary current, you could convert it to amps right off the bat. I didn't. I just left it in milliamps. I plugged this in. I got a current in milliamps. And then at this point, I converted to amps. However, if you just applied the correct number of sig figs and you left this in milliamps, that would be a fully correct answer on an exam. Now, the last group deals with circuits that are combinations of resistors, inductors, and capacitors. I'm only ever going to ask you about circuits that involve two of those. So the first one here is just an RC circuit. These are the ones that we encountered first chronologically. I think it's the second half of the Fundamentals of Circuits chapters where we see this. So I have an initially uncharged capacitor, battery, and resistor that are connected in series, like is shown here. Find the charge on the capacitor after one time constant has elapsed. An easy mistake to make with RC circuits is conflating the discharge expression with the charging expression. So the discharge expression does not have this 1 minus the exponential decay term. This is something that only needs to be accounted for with the charging expression. So I know that eventually this capacitor is going to match the potential difference of my battery. So eventually it's going to get to 12 volts. So I can use the capacitance value, which is given, that's 2.0 microfarad, and I can figure out how much charge is on the capacitor. So I have 2.4 times 10 to the negative 5 coulombs of charge. That's going to be the maximum. So the time constant for an RC circuit, tau, is just the resistance times the capacitance. And I didn't show it broken down here, but if you break down an ohm and a farad, you're going to end up with everything canceling except for 1 second. So my time constant is 1.0 times 10 to the negative 5 seconds. I can plug that in here, and since I'm trying to figure out the charge after one time constant has elapsed, that just means that lowercase t and tau have the same magnitude so that their ratio is going to be 1. So I can just plug in a 1 there, and I end up with a charge of 15 microcoulombs. I could leave that as 1.5 times 10 to the negative 5 coulombs, but since this is this time matches up with a delta V that is less than 12 volts. So in other words, by the time one time constant has elapsed, this capacitor is not completely charged yet. So I get 15 microcoulombs as opposed to 24 microcoulombs, which is what I would get if I converted to microcoulombs here. So the capacitor is still charging, in other words. For 22, let's assume that our capacitor is completely charged. Now we're going to let it discharge, and we want to figure out how long it takes for the current to reach 20% of its maximum. So the current, let's see, I think I have, this should probably say charge. Sorry. So we could derive an expression that would answer the same question for current, but it would not be Q being based on Q max, but instead I being based on I max and so on. So because we're just looking for essentially a T final, if we calculate the charge at T final, that is going to give us the same information, or that's basically taking us one step away from figuring out what the current would be. So let's do that. We have Q being based on Q max and then the exponential decay term. So because I know I'm going for 20% of the maximum value, I don't really have to go back up here and plug in 2.4 times 10 to the negative 5 coulombs and figure out what 20% of that is. You could, but it's not required. So I didn't do it here. I just used that to cancel out Q max. I have the time constant, which is calculated from the previous question. So that goes into the denominator of the decay term. And I have 0.20 is equal to e to the negative this expression. Take a natural log of both sides. That will give you a negative value for a quantity that's less than 1. That negative will cancel this negative here so that you end up with time as positive. This is 16 milliseconds. So this is, let's see, that should be micro. I apologize for the typo there. But if this is times 10 to the negative 5, 16 microseconds would make sense. So for an RC circuit, the time constant doesn't control anything beyond the rate at which it takes for this system to charge or discharge. Eventually, you know that this capacitor will be capable of charging or it will be capable of discharging. But if you are trying to design something that meets a certain time standard, playing around with RNC would let you do that. For 23, we have an LC circuit. So we are imagining that we start off with our same capacitor from the previous problem, but it's uncharged. It is, charged after question 22. And it's got a potential difference of 12 volts. It's connected to an inductor. And the inductor is starting off uncharged. I believe we were given the inductance value, so that's 12 millihenry. We can bring that down. We want the maximum current in the circuit and the frequency of the resulting oscillation. We have a problem in our class notes. So the second half of the electromagnetic induction class notes has an LC circuit similar to this. And I think we were looking for a time or a period, not an angular frequency. So go to your angular frequency expression for an LC circuit. That's going to be 1 over the square root of L times C. So L times C multiplied together will have units of seconds. When you take a square root, second squared. When you take a square root, you'll get back to seconds. So I can plug and chug at this point. I have the units of inductance. So that's Tesla meter squared per amp. That's the same as 1 Henry. And I've broken down the farad into Coulomb seconds over Tesla meter squared. So the farad is something that we could write as the ratio of charge and voltage, so coulombs per volt. But instead of taking the volt all the way down to joules and coulombs, here I've written Tesla meter per second, or I've written a volt as Tesla meter per second. So 1 over a volt is seconds over Tesla meter squared. And you're going to get cancellation of everything except for the 2 seconds that are in the numerator. When they're underneath the square root, they're just going to yield seconds. And you're taking a reciprocal of all of this. So this is radian per second. So to 2 sig figs, it's 6,500 radian per second. Now for the maximum current, there is more than one way that you can calculate this. The notes that we have for electromagnetic induction part 2, I believe, shows 2 different ways you can do this, but I've just chosen energy conservation. So the energy stored in the magnetic field inside the inductor is just 1/2 the inductance times the square of the current. The energy stored inside the electric field in the capacitor is 1/2 capacitance times potential difference squared. So we can solve for the current based on the capacitance and inductance values you have and the potential difference of the capacitor at t is equal to 0. These units break down as such. I have coulombs per volt here. I didn't split that up the same way that I split it here, but the unit cancellation is going to be really similar. A volt is something I can write as a Tesla meter squared per second, so that's going to be squared. And then I break this amp into a coulomb per second. I'm going to be left with coulomb squared over second squared underneath that radical, so taking a square root is just going to give you coulombs per second, which is an amp. And to 2 sig figs, that's 0.15 amps. So that's the maximum current. But just as we saw when we discussed this in lecture, This would produce an oscillation. So as the capacitor is discharging, the inductor would be charging, and vice versa. So the current wouldn't be something that is constant over time, but instead it would oscillate. But this would be the maximum magnitude of the current. Now for number 24, we have an RL circuit, an inductor, and a resistor. The battery is connected there. We're pretty much using that so that we know that eventually the delta V across the inductor will be 12 volts, just like the battery. So when will the current in this loop reach 50% of its maximum value? So I am looking at a charging cycle here. I is equal to I max times 1 minus. This is exponential decay term. I could figure out what the maximum current would be, because that would just be this ratio of the EMF over the resistance. But just like we saw for a couple of questions earlier, I don't actually have to know what that value is because I'm looking for a percentage. So I just plug in the decimal 0.5 on the left and then 1 on the right. So I'm going to end up with a 0.5 here. And then on the right-hand side, if I take a natural log of both sides after basically subtracting this 1 off, or the way that I did it here is I added e to the minus t over the time constant to both sides and then subtracted 0.5 off, I'm going to end up with the natural log of 0.5. So that's still going to yield a negative value, but that negative is going to cancel this. So t over that time constant is going to give me the magnitude of the natural log of 0.5. And what I end up with here is legitimately 1.7 milliseconds. So not a unit conversion error like that previous question. Hi, everyone. This is a brief review of the content that's going to be on the Unit 3 exam. So that includes the current and resistance chapter, fundamentals of circuits, the magnetic field, and electromagnetic induction. As far as questions that you can definitely expect to see on the exam, I am going to give you a circuit that involves just one battery and multiple resistors, but there will be multiple loops. So I think the best thing that you could study is the problem from the end of the DC circuits lab. That's the one that we ended up having to do remotely, but the very last page involves a circuit that's neither completely parallel nor completely series. I'll let you know the directions of the current, so that's not something that you're going to have to guess. You're also not going to have to deal with multiple batteries, but it is crucial that you remember how to reduce the circuit, because the equivalent resistance rules for series and parallel are not interchangeable. So make sure you know which one goes with which situation. I'm going to give you a question about an RL circuit, an RC circuit, or an LC circuit. It won't be all three, it'll just be one of those, but it's easy to confuse the way you define the time constant, and it's easy to confuse how, particularly for the RC and LC, how the capacitor discharges or charges over time. So I would suggest that you review the last group of problems from the practice exam, also the last 2 problems from the electromagnetic induction class notes as well. The RC circuit was first introduced at the second half, or in the second half of the fundamentals of circuits class notes. I'm going to ask you something about current density and a junction. So imagine you have multiple wires feeding into a junction. If you use the law of conservation of current, you can figure out how much how much current is attributed to each wire, and remember how you can calculate current density. If you know the amount of current going through a wire, then the current density is something you can determine just by knowing the radius of the wire. I'll ask you about electromagnetic induction. So the big ones here are Faraday's law and Lenz's law. So Lenz's law more directly talks about the induced magnetic field direction and how it relates to the direction of the change in flux that may or may not be happening in a wire coil. So if flux is not changing, it does not matter how big the coil is. It does not matter how strong the magnet's field is. There simply will not be an induced EMF. But anytime the flux changes, then the induced EMF is going to be bigger than zero. And transformer relationships also fall underneath the electromagnetic induction umbrella. So make sure that you know how to compare the number of turns on the primary side of a transformer to the number on the secondary, and then make sure that you know how the potential difference across each coil relates to its opposite. So study the difference between a step up and a step down transformer, in short. And then also remember that you can use the law of conservation of energy on a transformer. So if you have enough information to figure out the power in your primary coil, that's got to be the same as the power in the secondary. And also I can promise you a question about the right-hand rule that won't involve any sort of calculation at all, just accurately being able to use both the thumb and fingers version that just tells you about the direction of a magnetic field with respect to a current carrying wire, and also the cross product version, where you can determine the direction of a force that a moving charge would feel so long as it was in the presence of some external magnetic field. So the normal exam rules will be in play on Monday the 27th. So I will have to leave early, but you will be able to take your exam down to the testing center if you are if you need more time than what I or Amy can accommodate for you. And then I can either get those exams later in the day, or if possible, can potentially get them from Amy later on. But you will be getting scans of any of the graded labs that I still had in my possession for you. So that might be a combination of labs that you initially handed in on paper, or labs that I might have printed out and graded on paper and then rescanned, because I can do that faster. So keep an eye out for that. If you have questions about anything, drop me a line on Canvas between now and Monday morning. And I kind of hate to step on your long weekend by having an exam right afterward, but I hope you got to sleep in a little bit later than usual on Thursday and Friday. Okay, you know how to get a hold of me if you have questions, so reach out if you need to.